Thank you. First, thank you also for the organizer and for our Japanese colleague who made the effort to come to Europe. Actually, in econometrics, we read a lot from Japanese economists, like standard textbook, econometrics, Fumio Hayashi. Also, when we learn stochastic calculus, Ito calculus, but we rarely meet for some reason economists, except when we are in the US, like Kitamura in Yale. But I'm very glad to see so many people from Japan here. So this is a talk about an old project. Part of it has been already published. We have several results that we have not published, and it's, as its names indicate, it's about partial sum processes of functions of ARMAX residuals. So this project actually started, when it started, it was not at all about ARMAX. It was about a kind of weird kind of Garch model. But this kind of weird Garch model, they had an ARMAX representation where we had to deal with a residual and with more precisely functions of residuals to make the inference. And it's how this project started. And here I will present a bit of it. So it's with a joint colleague from former colleagues of mine from Norway, Stefan. So let's talk about ARMAX. So ARMAX is just an ARMA model, so autoregressive moving average model with a X, which stands for any covariate that you can add in the models. And I would argue that at least in standard econometrics, it's probably one of the most common model. Why? Because first, it's nest linear regressions, which in economics is like almost everywhere. It nests ARMA models. It nests also VARMA model. You can write VARMA model as ARMAX. Actually, many nonlinear models, including switching with switching regime, they can have an ARMAX representation. So many models can be put into it. And here, so we don't restrict the model to be linear with respect to the covariate, so we can have it nonlinear. And actually, in the paper, we do more general than ARMAX, we do triangular array of ARMAX. So when you work with this ARMAX model, especially with the representation of other models in terms of ARMAX, you often need, and it was the motivation for the paper, is that you need to use, you would like to use error term, but of course you don't have access to the error terms, so you need to use the residuals. And like one of the working example that we use in the paper, but there are many other examples that we could use is, for example, QSUM tests, when you would want to detect a structural break in a time series. And this is used like in medical science, in machine learning, when they want to change the algorithm. It's used in many setups. And more generally, when you use two-step estimation procedure, you need to use the residuals. So regarding that, there are several results in the literature. Actually, there are many of them. And but the results that I know at least, they often make quite some assumption on the errors. Actually, they make standard assumptions. So the basic result, they assume IID or Martingale difference, but they are, to my knowledge, there is no result when, for example, you allow autocorrelation in the error terms, which you get when you use the ARMAX representation, or even if you just assume weak white noise. So there is no, as soon as you try to relax a bit the assumption on the errors, you don't have so many results. Also, except for a paper by Bay, you often assume finite variance errors. And on the top of that, all the results I'm aware of, they don't allow for covariates, like for example, time trend and so on. And here we can deal with all of that. And so our main contribution is to provide, so here I assume that the function is the identity, but actually we could deal with function, but since we have not published and I did not have time to type the slides, so I did not put it. But basically the general object we are working with is like this process. So it's a process indexed by S, and this S determines how many like what is the fraction of residuals you are looking at in this average. And here I repeat, like I put just the residual, but we have result also for function of residual or function of block of residuals. Can do it. So why? So like these projects, first, when we looked at the literature, people, they make this probabilistic assumption and they use kind of probabilistic inequality that are a bit slightly high level. And here we managed to generalize a lot this result and get rid of many assumptions, because we really like went back to very basic inequalities. We have one Hungarian inequalities, which is a bit complicated, but the rest is like really like, or sometimes we even use like sigma additivity of measures. It's very low tech in some sense. And thanks to that, we obtain a very versatile toolbox, and we can deal with many cases that that are not dealt with in the literature. So here is the outline of the talk. I will. So I don't know how much minutes I've already talked a lot, I guess. Okay, that's fine. So so I've already talked about the motivation. So I will first, in the first part, I will just talk about how to deal with the ARMA part. So in the ARMA-X, it's like an ARMA, so autoregressive moving average, and you have this X part. And so I will show that we have a simple lemma that allows you to separate what comes from the covariate, which can be kind of arbitrary, and what comes from the ARMA. And then I will give some result, one slightly exotic result with an ARMA with infinite variance. We have many other applications in the paper or in LaTeX. Then I will focus on the X parts, so these covariate parts, which can be, for example, a time dummy, which can be a trend, that can be several things. Actually, this X parts is also, so as you will see, we can really play with it in the sense that in some cases, we can even, for example, when we want to deal with unit roots, for example, we can put the unit roots in the X parts to facilitate like the to deal with the unit roots. And that's actually what I'm going to do in the third part. And I will also give an application which is like quite straightforward, where you want to do the density estimation, non-parametric density estimation of the ARMA-X errors. And then I will conclude. So before I dive further in the paper, so the general takeaway message, if you just leave the room now and you don't want to read the equation and you just want to use R to do some applications. So there are three takeaway messages of this presentation. The first is that as long as you do estimation, most of the time, at least under standard assumption, if you replace the unknown, the unobserved error term by the residual, you are typically fine if you do estimation. So if you think about over regression, you have this error term, but of course you don't observe, but you can get the residual. If you treat the residual as an error term, for estimation, usually you are fine. For inference, that's not the case. So when you move to testing and inference, typically if you replace the residual, like the error term by the residual, then typically it's not going to work. And the intuition for that is that when you move from estimation to testing, especially in classical, when you are not as sophisticated as some people in this room, we just move from basically the law of large number from the central limit theorem or refinement of the law of large number of refinement to the central limit theorem. And when you do that, basically you scale by square root of t. And basically it means that you blow up the difference between the error and the residual, and then it causes trouble. So, and even in very simple example, and I will come back to a very simple example, which I think provides most of the intuition behind the result, even if you need many more pages of proof to get the same thing. And so, and given these two kind of salient feature, what this paper is doing is that it provides a very low-tech versatile toolbox to deal with the inference. So first, this toolbox allows you to check when it is fine to replace the errors by the residuals, even for inference. So there are some cases. So for example, if you have infinite variance, because the rate of convergence is faster, it can work out. And if it's not the case, we characterize kind of this difference, kind of this gap, that asymptotic gap that appears. And we provide an algorithm. So I'm not sure I will go through the algorithm. I'm not sure I have it in the slide, but we provide an algorithm to remove this gap between this asymptotic gap that is due to the difference between residuals and the error. And then we and how to get this asymptotic distribution fine by removing this gap. So by the way, feel free to ask questions during the presentation. I'm fine. Actually, I prefer that you ask questions during the presentation, but I have a clue whether it makes kind of sense to some people what I'm saying. What is an ARMAX? So as I said, it's just let's take a standard like what you read in Brockwell-Davis or standard textbook. So it's an ARMA. So here it's like the autoregressive part. So it's an AR, sorry, with an MA part. Sorry, with this pointer I have a bit problem. And on the top of that, you allow for covariates. And here we made the standard assumption about this. So this phi b and this theta b are like this lag polynomial that allows to write this in a kind of compact way. So here we are a bit more general. I don't think I will explain why, because I don't like in the example I will provide you. It's not needed, but our result apply to a triangular array. That means that it's why you have this double index here, so that the covariates and the why they depend on the sample size. It's useful. Basically, it's useful when you have when you do kind of an infill asymptotic. For structural breaks, that's one way to motivate it. And then the residual, how you define the residual is very basic. It's like in regression, it's like you take the observed value minus the predicted value. And this is how you get the residuals. So here it's basically yt minus mu hat, and you'd minus the predicted. So you replace everything with the predicted, and you get the residual. Of course, for negative time index, you need to have a convention, and here we follow a convention, which is to, since we cannot go backwards, we cannot go in the past of the first data, we need to set a value, and we set 0. So, and here, what is kind of in our setup, so we don't need to specify what is your estimation method. We don't know whether it's maximum likelihood or pseudo-maximum likelihood or method of moment or what estimating function. The only thing that we require is that the rate of convergence is the least as fast as square root of t. So it means that if you have a unit root when it's faster, you are fine. If you have an infinite variance where the rate of convergence is faster, you are fine. No assumption. And basically the questions, so if we assume that the function is the identity, is like how these objects differ, how the partial sum of the residual differ from the partial sums of the errors. And here again, so here I just take the residual and the error, but I could take the function of the residual and function of the error, and we can deal with that also. And please bear in mind, so we will use the notation that this partial sum of the error is like this calligraphic Q, and the partial sum of the residual will be this calligraphic U hat. At some point in all this math paper, you run out of the letters, so you have to come up with some. So I don't want to put some Hebrew, so that's how we did it. So just to come back to the literature, so actually this paper is a bit weird because the techniques. You could have written this paper in probably the 70s, but people started to think about this type of problem so in regression, it started earlier, especially with empirical processes. But for the time series, it started essentially with a paper by Bay. And basically, his result was that it does not matter if you replace the error by the residuals. But why it was the case is because he was implicitly assuming a zero mean ARMA. And it can look like a bit like weird to assume that you take a process and it will have a zero mean. But remember that in time series, for example, if you take Brockwell-Davis of classical, typically you always recenter your process. And the idea is that it does not matter. But here, actually, it's a case where it matters. So you need to be careful. And actually, that was probably shown like clearly beyond the regression context by you and Lee, who showed that actually as soon as you have, as soon as it's not zero mean, as soon as you have a mu, basically the difference between the partial sum of the residual and the partial sum of the errors is not disappearing asymptotically. You have a gap, and they characterize the gap in this way. And please bear in mind is that it's like even if your ARMA is zero mean, but you don't know that the mean is zero, you will have this problem. So basically, the Bay result in practice, it was almost useless because he assumes that implicitly he did not know probably at that time, but he implicitly assumed that it's zero mean and that you know that it's zero mean. So so as soon as you don't assume that you know that it's zero mean, basically you have this gap that appears. And actually, you showed that in this case, under a stronger assumption than ours, that you can like apply a simple transformation, and it's just average correct the residual to get rid of this asymptotic gap between the residual and the errors. So just to make justice to the literature, so here we approach this problem from the point of view of the ARMA and from this partial sum. There is another literature that is approaching the problem from the empirical process literature. Here the advantage that you will see is that we have very little assumption in a probabilistic assumption, but of course we will have some cons in the sense that when you have the empirical process, you have all empirical process, so you can do also many things that we cannot do, and vice versa. So what are the assumptions? So we make. So here I will state all the assumptions we make because I think they are pretty relatively transparent and pretty weak. I think it's one of the strong aspects of this paper. At first, so we assume that basically the ARMA is what we say causal and invertible, which means that all the roots of this lag polynomial, they're outside the unit root. So again, so this assumption just means that when you write the ARMA-X process, in this way, we don't want to have like unit root here and unit root here. But the trick but it doesn't mean that we rule out actually unit roots or roots inside. It's just that if you have this kind of roots, you need to put them in the X part. So it's just a question of representation. Then, second assumption, which I've already hinted at, is that we ask that at least your parameter estimate convert the square root of t. It can be faster, but it cannot be slower. But we don't care which estimation method you use. And finally, the third type of assumptions, we require that the error term has moments 1 plus epsilon. So we can have infinite variance, but we need, for example, the Cauchy won't work. I'm sorry. We don't like actually we knew how we could do, but we changed the math a bit. But in this case, we assume that like at least you have a first moment and a bit more than the first moment. And then we have this assumption 3b, which I will show later is quite weak. Basically, like this assumption 3b's, if you have if the strong law of large number applies to the error term, you are fine. So you can have autocorrelation and so on. But I will provide more like a list of assumptions that allows us to check this assumption 3b. Under this assumption, basically, we can exactly characterize the asymptotic gap between the partial sum of the residuals and the partial sum of the errors. And this asymptotic gap exactly corresponds to these two terms. So before going a bit further, just to provide, that's maybe with the takeaway message slides and this slide, if you know these two slides, probably you know as much as me, more or less. So this slide is just an example to show where, like like I think in this simple example, you see everything, why it works and why it does not work. After, okay, you can do the proof and generalize. But here you see like more or less what makes stuff work and what makes stuff, what can be the problem. So let's take the simplest model I know. And the simplest model I know is just that you say that your random variable is a constant plus an error term. Then we know, basic stats or basic econometrics, that the OLS estimator of mu is just the average. Then we can, once we have this estimator of mu hat, the residual is very simple. It's just the realized value minus the predicted value. And here the predicted value is just mu hat. So it's just the average. And if you, so if you replace now y tilde t by its actual value, it's mu plus ut minus mu hat. Everybody agrees with that? Then now if you subtract, so this is the residual, if you subtract to the residual the actual error term, you get exactly mu minus mu hat. And here you can already see that by the law of large number, as long as the law of large number holds, the difference between the two will go to 0. But if you multiply this difference by square root of t, basically it will converge to a Gaussian typically. Except if you have some rate of convergence, so then it will blow up. You will have an asymptotic gap. And that this is basically like what happened in more complicated case. And of course, in more complicated case, you need to characterize this gap, and it's more complicated, and you need to use more tricks to get rid of this gap. But that's basically like the essence of what's going, of the mathematics that are behind. So if you want, I can be more explicit. So since you are not really interested in the residual minus the error, but on the partial sum of the difference, you can take the partial sum. And here, okay, 5 minutes, so you get exactly this. And here you can already see that actually if we knew that mu is equal to 0, like in the case that was treated in the first paper, then it means that mu hat is also 0 because you know, and then there is no asymptotic gap because 0 times anything is 0, so there is no asymptotic gap between the two. Okay. This is what is, I can go in more detail, I think. So I have 5 minutes. So let me just tell you why we think, when I was telling you that the assumptions are pretty weak in this paper, and that here maybe the only one you might wonder is this one, and why this assumption is satisfied under very general condition. I will provide you 2 catalogs of assumptions that allows you to check it. And the first one is just that, so it's not a long range, it's the opposite of long range, sorry. It's just that the autocovariance goes, if it decreases geometrically, then the assumption 3b, A3b is satisfied. So it's, if you have an ARMA standard, it will be satisfied. And of course, this is satisfied by weak white noise, IID, causal ARMA, and so on. The second catalog of assumption is that if the UT satisfies a kind of strong law of large number, which in the case of ergodic stationary, in the case of a stationary process is just that you need that it's ergodic, then it's done, then it satisfies. And of course, you get this if you have alpha mixing and part angle difference and so on. So the assumption is, so it means that basically we allow in the error term to have autocorrelations and many things going on. And if you are, like Vitote, you are wondering about like long range dependence, you can have long range, but you need to have a lot of large numbers still to hold. So you should not destroy the ergodicity. It's still So I have how many? 3 minutes. Okay, maybe let's just not forget about the X part and just do infinite variance case for the fun of it. So when you have infinite variance, what happens is that because you have a lot of variability in the data, you learn faster, and typically your rate of convergence is faster than square root of t. And actually you have very little result on ARMA with infinite variance, except this paper by Mikosh and co-authors, where they get a rate of convergence of t log t power 1 over alpha, with alpha strictly smaller than 2. And in this case, actually, since the rate of convergence is quite fast, actually, we show that in the Skohorod topology, basically, the difference between the partial sum process of the residual and the partial sum process of the errors kind of disappear asymptotically. And it makes sense because you learn fast, because you have a lot of variability because of infinite variance. And so then in this case, it's one nice case where the result of Berry holds. The proof is pretty easy once you have first lemma, but let's skip it. So just often when you look at this literature about infinite variance, the big problem is that actually you don't know this alpha. This is a bit like the mystery. So if you have a lot of data, you can do it graphically, but you don't know too much about this alpha. So here we don't want to assume that we know the alpha. So we use a trick that was used by Jin and co-author in 2009. And the usual trick is just that you divide by the rate of convergence, multiply and divide, so that these two, basically the rate of convergence simplifies and it does not affect your asymptotic distribution. And so you get something pivotal with respect to the rate of convergence, but the distribution, we don't know exactly how it looks like, so we need to use subsampling, but this is not a problem. Computers, the first century. Okay, can 1 minute? Okay, so here after so just maybe summarize. So we show like in this how to deal with the X part, and in general it can be seasonal dummy, generic X, and then so just give you the idea. So how you deal with the X part? Basically, you transform the X so that it looks a bit like the error term, but in a way that you can still characterize the limits, and you can deal with, since our toolbox is very low tech, we can deal almost with any X we could encounter, at least in econometrics, which is like seasonal dummy or like stuff like that. So let me skip that. And maybe let's provide maybe an application for people who are interested in kernel estimation. So often, and actually that's often the case also in, so Markana, he had a talk where they assume like exchangeability, but when you have time series, when you have dependence, first you need to extract the dependence, for example, using an ARMA, and then it means that you are working with the residuals. And if you want to estimate the kernel density, you need to make sure that it works, because again, you are replacing the error term by the residuals. And here we have a result relatively general that tell you that actually you can do it under pretty general assumptions. So if you have your kernel estimator of the density, and here it's with the error term, and instead of using the error term, you are using the residual, you still get a uniform convergence. Like the difference is going to zero asymptotically. We have also some result if you are interested in polynomial time trend and unit root, but I think I will run out of time, so I will skip it. Just go back. So in conclusion, ARMAX is one of the most common class of model, at least in econometrics. In consequence, we need to use partial sum of residuals in many inference procedure instead of a partial sum of the errors. And here we provide a versatile and relatively low-tech toolbox to work with difference under minimal assumptions. And we have, more general result, but let's forget about it. Thank you. And